Chapter 1: Acids, Bases and Salts. Acids, bases and salts are substances that dissociate in solution of water to form charged particles or ions, that is, cations and anions. Consider water. When water dissociates, it breaks into equal number of hydrogen ions and hydroxide ions. In contrast, when certain other substances dissociate, they may release more hydrogen ions or more hydroxide ions. For example, hydrochloric acid releases more hydrogen ions when it dissociates, and sodium hydroxide releases more hydroxide ions when it dissociates. Depending on its concentration of hydrogen versus hydroxide ions, a substance can be classified as either an acid or a base. The pH scale measures how acidic or how basic a substance is. It ranges from 0 to 14, with 7 being neutral. When a substance has a pH of 7, like water does, it releases an equal concentration of hydrogen ions and hydroxide ions. When a substance has a pH greater than 7, it is classified as a base and releases a greater concentration of hydroxide ions. The more the hydroxide ions released, the more basic the substance. When a substance has a pH less than 7, it is classified as an acid and releases a greater concentration of hydrogen ions. The more the number of hydrogen ions released, the higher the acidity and the lower the pH. We start with acids. An acid is any substance that releases hydrogen ions as the only cations when dissolved in water. For example, hydrochloric acid, when dissolved in water, liberates a hydrogen ion and a chloride ion. Acids are classified as organic and inorganic acids. Acids obtained from foods like curd, lemons, grapes, raw mangoes, citrus fruits, and gooseberries are called organic acids. Hydrochloric acid, sulfuric acid, and nitric acid are called inorganic or mineral acids. Acids turn a blue litmus paper red, and they also turn methyl orange red. They have a corrosive action on the skin. Sulfuric acid stains the skin black. Nitric acid stains the skin yellow, and hydrochloric acid leaves an amber stain on the skin. Acids can conduct electricity because of the free ions. They generate heat when diluted. And now we look at strengths of acids. Consider these two beakers, one containing 2 molar ethanoic acid and the other 2 molar hydrochloric acid. Then we add an equal amount of calcium carbonate. As you can see, the reaction is more vigorous for the case of hydrochloric acid. Mineral or inorganic acids are described as strong acids, while inorganic acids are termed as weak acids. Strong acids dissociate completely into ions, while weak acids dissociate partially. Strong acids therefore have a higher concentration of hydrogen ions in solution than weak acids. Therefore, the pH of strong acids is usually lower than that of weak acids. Strong acids are also better conductors of electricity compared to weak acids. Concentrated versus dilute acids. Concentrated hydrochloric acid is produced when hydrogen chloride gas is dissolved in a small quantity of water. If the same volume of hydrogen chloride gas is dissolved in more water, the acid is said to be dilute. Therefore, an acid is considered concentrated or dilute depending on the amount of water present in it. Chemical properties of acids. Reactions with metals. In this experiment, we have zinc granules in a test tube. Then we add 2 milliliters of sulfuric acid. We see that a gas is liberated. And when a burning splinter is brought close, a pop sound is produced indicating its hydrogen. So acids react with metals to form salt and hydrogen gas. Reactions with carbonates. In this experiment, we have 1 gram of magnesium carbonate in a test tube. We pour 2 milliliters of hydrochloric acid. We observe that a gas is being evolved. When bubbled through freshly prepared lime water, which is calcium hydroxide, a white precipitate is formed, indicating it's carbon 4 oxide. And so acids react with carbonates to form salts, water, and carbon 4 oxide. Reactions with hydrogen carbonates. In this experiment, we have 2 grams of sodium hydrogen carbonate in a test tube. We add 2 milliliters of hydrochloric acid into the test tube. We see that a gas is evolved. When passed through calcium hydroxide, a white precipitate is formed, indicating it's carbon 4 oxide. And so acids react with hydrogen carbonates to form salts, water, and carbon 4 oxide. Reactions with metal oxides. We take 10 milliliters of hydrochloric acid in a beaker, and then we add 2 grams of copper 2 oxide. We stir the mixture continuously. The black solid disappears and a blue-green solution is formed. This solution is copper 2 chloride. And so acids react with metal oxides to form salts and water. Next, we look at bases. A base is any substance that dissociates in water to produce hydroxide ions as the only negatively charged ions or anions. For example, sodium hydroxide, when dissolved in water, dissociates into sodium ions and hydroxide ions. Bases turn red litmus blue. They have a slippery or soapy feel when touched because they dissolve the fatty acids and oils on the skin and reduces the friction between your fingers. Like acids, bases can conduct electric current due to existence of free ions in their solution. They also liberate heat when diluted with water. Bases can also be categorized into strong and weak bases. A strong base completely dissociates into a metal ion and the hydroxide ions in aqueous solutions. Strong bases like sodium hydroxide and potassium hydroxide are corrosive and can burn the skin. A weak base does not ionize fully in an aqueous solution. And so strong bases have a higher concentration of hydroxide ions, and thus their pH is usually higher than that of weak bases. Strong bases are also better at electrical conductivity compared to weak bases. Bases such as magnesium hydroxide and copper 2 hydroxide are weak bases. Suspensions of magnesium hydroxide in water, often called milk of magnesia, are used as antacids to neutralize stomach acid. Bases such as sodium hydroxide are soluble in water and are called alkalis. Some bases are insoluble in water and are not alkalis. And so all alkalis are bases, but not all bases are alkalis. Reactions of bases. When a base like sodium hydroxide reacts with a metal like zinc, it liberates hydrogen gas along with formation of a salt called sodium zincate. And so bases react with metals to form salts and hydrogen gas. Consider carbon 4 oxide bubble through calcium hydroxide, which is a base. It results in formation of calcium carbonate and water. Bases react with non-metallic oxides to form salt and water. This is very similar to a neutralization reaction between an acid and a base because non-metallic oxides are acidic in nature. Acid-base reactions. An acid reacts with a base to produce salt and water with the evolution of heat in a process called neutralization. In this process, the properties of the acid and the base disappear. Consider a 10 milliliter solution of dilute sodium hydroxide, which is a base in a beaker. In this solution, we add a drop of methyl orange indicator. The solution turns yellow in color. Now we add a few drops of hydrochloric acid and stir the mixture. We continue adding the acid drop by drop while stirring until at a point where the solution just turns pink. The change in color indicates that the acid has neutralized the base, so the solution is neutral. This is called the endpoint. If we heat the solution, the water evaporates and leaves a residue, which is sodium chloride, but of course contaminated with the methyl orange indicator. Now, before we look at salts, let's talk about polar and non-polar substances. Consider the structure of a water molecule. A water molecule is made up of an oxygen atom and 2 hydrogen atoms that are covalently bonded or share electrons. However, the electrons are usually not equally shared between the atoms. Electrons have a higher probability of being near the nucleus of the oxygen atom, giving that end a slightly negative charge. And so effectively, the hydrogen atoms of the molecule will have a slightly positive charge. These charged ends weakly attract the positively charged ends of other molecules, forming hydrogen bonds. The hydrogen bonds are constantly formed and broken all the time. A molecule that behaves as if it is negatively charged on one end and positively charged on the opposite end is said to be polar. Water is therefore a polar substance or a polar solvent. In hydrogen chloride, the chlorine end is partially negatively charged, while the hydrogen end is partially positively charged. So when hydrogen chloride is added to water, the chloride end is attracted to the hydrogen end of the water molecule, while the hydrogen end is attracted to the oxygen end of the water molecules. This causes the hydrogen chloride to dissociate into hydrogen and chloride ions. The increased concentration of hydrogen ions makes the solution acidic. Usually, polar solvents only dissolve polar substances. Non-polar solvents dissolve non-polar substances. For example, in this experiment, we have potassium manganate 7 crystals, iodine crystals, carbon tetrachloride solution, and water. We take 2 beakers and pour equal volumes of water in them. Then we take 2 other beakers and pour an equal amount of carbon tetrachloride in each. Now we take some potassium manganate 7 crystals and put in one of the carbon tetrachloride solutions. We add some potassium manganate 7 crystals to water as well. Again, we put some iodine crystals in carbon tetrachloride and some amount in water. We see that the potassium manganate 7 crystals do not dissolve in carbon tetrachloride, but the iodine crystals do. However, potassium manganate 7 crystals dissolve in water, but iodine crystals do not. And this is because potassium manganate 7 and water are polar, so potassium manganate 7 dissolves in water. Iodine and carbon tetrachloride are non-polar, so iodine dissolves in carbon tetrachloride. Polar solvents cannot dissolve non-polar substances, and neither can non-polar solvents dissolve polar substances. And now we move to salts. Now, when we talk about salts, we do not mean just regular table salts. We are actually referring to a wide spectrum of ionic compounds. Some of these salts, like table salts or sodium chloride, are soluble in water. Others, like barium sulfate, are insoluble in water. Preparation of soluble salts. There are usually 2 common methods for preparation and isolation of soluble salts. Copper 2 sulfate is a common salt, either as crystals or in solution. We can make our own copper 2 sulfate. We put 2 spoonfuls of copper 2 oxide, that is the black powder, into a beaker. And then we add sulfuric acid and mix them with a glass rod. The rate of dissolution is slow, but when heated on a Bunsen flame, the solution turns blue. To ensure that all the acid has reacted, confirm that there are some unreacted copper 2 oxide. In this process, copper 2 oxide reacted with sulfuric acid to give copper 2 sulfate and water. As copper 2 sulfate is soluble in water, a solution is formed. Copper 2 oxide is a metal oxide, which is an insoluble base, and sulfuric acid is an acid. So what happened is an acid-base neutralization reaction where a salt and water have been formed. An acid-base neutralization reaction is a type of a double displacement reaction. And so the copper 2 and hydrogen ions have switched to form copper 2 sulfate and water. So a soluble salt can be made by reacting an insoluble base with an acid. The unreacted copper 2 oxide is removed by filtration. The next thing is to obtain solid copper 2 sulfate from the solution. We evaporate water over a Bunsen flame, but not to dryness. We place the saturated solution in a crystallization dish, and after some time, copper 2 sulfate crystals are formed. Soluble salts can also be made by reacting a soluble base or an alkali with an acid. For example, we can make sodium chloride by titrating hydrochloric acid with sodium hydroxide. Remember to add phenolphthalein indicator so that we know the endpoint of the neutralization. However, we do not want pink crystals, so we take note of the volumes of the acid and alkali used in the initial titration, and we repeat the process without the phenolphthalein indicator. This is also a double displacement reaction in which the hydrogen and sodium ions have switched. As sodium chloride is soluble in water, we get a solution of sodium chloride. This is also an acid-base neutralization reaction, yielding a salt and water. We evaporate as much water as possible and then let the sodium chloride crystallize. So there you have it, 2 soluble salts by acid-base neutralization reactions.